A colossal block of granite sits in an ancient quarry, abandoned for thousands of years. This stone, and others like it around the world, represent one of history's most enduring puzzles. From the staggering foundations of Baalbek to the silent giants of Easter Island, our ancestors cut and moved mountains of stone with what seems like no tools at all. How did they do it? The central challenge is granite itself, a rock so hard it defies simple explanation. This video will reconstruct the precise methods ancient engineers used to conquer this impossible material, separating compelling evidence from pure speculation. We will examine how they quarried single blocks heavier than 10 buses, and what techniques might have slid an 800-ton stone into place. The stakes are understanding a lost chapter of human ingenuity. What does it truly take to move a mountain when all you have is rope, wood, and determination? The true scale of their achievement only becomes clear when you understand what they were up against. Granite is not just any rock. It is a titan among stones, forged under immense heat and pressure deep within the earth. Its beauty and strength made it the ultimate choice for monuments meant to last for eternity. But those same qualities presented a nightmare for the engineers tasked with working it. To appreciate their genius, we first need to grasp the fundamental challenge of the material itself. Think of the stones ancient civilizations commonly used. Limestone and sandstone are sedimentary rocks. They form in layers like a book pressed under the weight of time. This layered structure means they can often be split along natural planes with relative ease. A skilled worker with a simple copper chisel and a wooden wedge can make impressive progress, but granite is a different beast entirely. It is an igneous rock, born from molten magma that cooled slowly, allowing large, interlocking crystals to grow. These crystals, primarily of quartz and feldspar, fuse together into a dense, unyielding mass. There are no natural layers to exploit, no easy grain to follow. It is a chaotic, three-dimensional puzzle of mineral bonds, each one incredibly hard. This crystalline structure gives granite two defining characteristics. First, its legendary hardness. On the Mohs scale of mineral hardness, where talc is a 1 and diamond is a 10, the quartz in granite ranks a 7. That means it can scratch glass and steel. For an ancient artisan, this meant their bronze or even early iron tools would blunt against the stone faster than they could cut it. Simply striking the surface with a metal chisel would often just powder the tool's edge, leaving little more than a scratch on the granite. Second, and just as important, is its toughness. Hardness is about resistance to scratching, but toughness is about resistance to breaking. Granite possesses both. Its interlocked crystals act like a microscopic chainmail, distributing force and resisting cracks. You cannot simply whack it with a hammer and expect a clean break. It shatters unpredictably, creating useless rubble. So the ancient engineer faced a paradox. They needed a material of supreme durability for their temples and statues, yet that very durability made it seem nearly impossible to work with the tools we traditionally attribute to them. This was the fundamental puzzle. How do you cut, shape, and move a substance that laughs at your hardest metal? The answer lies not in a single magical tool, but in a profound understanding of the stone's own nature and a clever application of very basic physics. The Unfinished Obelisk in Aswan, Egypt, gives us a raw, unfiltered look at the ambition of these builders. Still lying in its granite bed, it is a single piece of stone that would have stood over 130 feet tall. If completed, it would have weighed around 1,200 tons. To put that into perspective, that is heavier than 200 full-grown African elephants, or roughly 10 fully loaded city buses. This was not just a stone, it was a skyscraper intended to be carved from a single, flawless piece of earth. but the scale becomes almost incomprehensible when we travel to the ruins of Baalbek in modern-day Lebanon. Here, in the foundation of a Roman temple, rests a trilogy of stones known as the Trilithon. Each one is estimated to weigh around 800 tons. These are not rough blocks, they are precision-dressed giants, fitted together so tightly a razor blade cannot slip between them. They were quarried over half a mile away and lifted over 20 feet onto a platform. The largest stone at the site, however, lies abandoned in a nearby quarry. Known as the Stone of the Pregnant Woman, it weighs a staggering 1,650 tons. That is equivalent to 3 fully fueled Boeing 747 jumbo jets. The logistics of moving such a mass, even with modern machinery, would be a monumental undertaking. On the remote island of Rapa Nui, the story repeats with a different character. The famous Moai, those enigmatic stone heads, are actually full bodies carved from compressed volcanic ash. The largest one ever erected, named Paro, stands over 30 feet tall and weighs approximately 82 tons. Yet an even more colossal figure lies unfinished in the quarry, nicknamed El Gigant. At nearly 70 feet long, it is estimated to weigh over 270 tons. The islanders not only carved these giants, they then transported them miles across rugged terrain to stand on coastal platforms. Each of these examples, from the deserts of Egypt to the mountains of Lebanon to the isolated Pacific island, presents the same visceral question. How do you even begin to manipulate a physical object of such absurd density? The numbers alone tell a story of a challenge that borders on mythology. The evidence of their struggle is written directly into the stone. To understand their methods, we must first visit the ancient quarries themselves, where the story of these megaliths truly begins. The initial challenge was not moving a block but creating one, detaching a single multi-ton piece of granite from the unbroken mountain. This was a surgical operation performed on a geological scale, and the tool marks they left behind are our primary clues. At sites like Aswan and Baalbek, you can still see the precise outlines of intended blocks marked out on the living bedrock. The first step was to identify a weakness, not in their tools but in the stone itself. Even the toughest granite has natural fracture lines, planes of weakness formed as the rock cooled and contracted over eons. Ancient engineers became master geologists, learning to read the stone like a map. They would search for these natural seams, these potential fault lines, because working with the rock's own structure was infinitely easier than fighting against it. Once a suitable section was identified, the real work began. They did not try to cut the block free from the top down. Instead, teams of workers would begin carving a deep, narrow trench completely around the perimeter of the chosen stone. Using nothing more than handheld pounders made of dolerite, a stone even harder than granite, they would pulverize the crystalline surface grain by grain. This was a process of incredible patience and exertion. A worker would swing the heavy stone hammer, striking the granite to create a small patch of dust and sand. This debris was then cleared away, and the process repeated for months, perhaps even years, to cut a trench that might be only a few inches wide but several feet deep. These trenches, still visible today, outline ghosts of obelisks and blocks that were never freed. But how do you separate the bottom of this giant stone from the bedrock below? The answer reveals a profound application of simple physics. After the trenches were deep enough, workers would tunnel underneath the block, carefully leaving a series of stone pillars to temporarily support its immense weight. Then, using wooden wedges, they would begin the final act of liberation. Dry wooden wedges were driven into small channels cut along the base. Then, water was poured over them. The wood swelled slowly and with immense steady pressure pushing against the granite. This swelling force, distributed across many wedges, would stress the rock along its natural fracture lines until, with a deep groan, the entire block cracked free from its cradle. This method left a telltale signature, a quarry floor that is relatively smooth compared to the rough, pounded walls of the trenches. It was a victory of leverage and understanding over brute strength, proving that the first and deepest cut was not made by a blade but by an idea. That deep groan of cracking stone was the sound of a problem solved, but only the first of many. Now, with a multi-ton block of granite successfully separated from the earth, the ancient engineer faced the next critical task, shaping this rough mass into a precise, usable form. Pounding method used for quarrying was far too crude and slow for fine work. For this, they employed a more refined and brilliantly simple technique, one that turned the stone's own toughness against it, the wedge and feather method. This was the scalpel to the quarry's hammer, allowing for controlled, predictable splits along exact lines. The principle is beautifully straightforward. You do not try to cut through the granite, you convince it to break exactly where you want it to. First, a line of small holes would be carefully drilled or pounded along the desired fracture path. This was painstaking work, again using those hard stone hammers or, in later periods, simple metal drills. Each hole was spaced just a few inches apart. Then, into each hole, the worker would place a pair of curved metal shims called feathers, which acted as a sleeve. Between these two feathers, they would insert a narrow, dry wooden wedge. The setup would be repeated down the entire line of holes. The final act was one of patient, controlled force. Water was poured over the line of wooden wedges. As the wood absorbed the moisture, it began to swell, but it was constrained by the hard metal feathers on either side. This confinement is the key. The swelling wood had nowhere to go except outward, pushing the metal feathers against the walls of the granite hole with tremendous, steadily increasing pressure. This force is not a sudden blow, but a constant, inexorable push, multiplied across every hole in the line. The stress builds within the stone, concentrating along the line of weakness created by the drilled holes, until the granite's own crystalline structure gives way, producing a clean, straight fracture right where the engineer intended. The archaeological evidence for this is not just speculation, it is etched in stone. In ancient Egyptian quarries, particularly in Aswan where the red granite was prized, you can find discarded blocks and quarry faces marked with these very lines of small, round holes. Some blocks even show partial fractures where the technique was tested or abandoned, providing a perfect cross-section of the process frozen in time. Similar evidence appears in Roman quarries across the Mediterranean. This method was so effective and reliable that, in principle, it remained in use for centuries, with blacksmiths making iron feathers and wedges that are nearly identical to those used by stonemasons well into the modern era. It demonstrates a fundamental shift in thinking from trying to defeat the stone by force to guiding its breakage with intelligence. The wedge and feather method did not cut the granite, it asked the granite to cut itself. But even the most precise fracture leaves a rough, uneven surface. For the final shaping, the smoothing of a curve on a statue or the perfect flatness of a block, meant to fit without mortar, ancient craftsmen had another surprising tool in their kit, one that harnessed a destructive force as old as humanity itself, fire. The concept is known as fire setting, and it is a dramatic example of using a material's own properties against it. The principle relies on a simple physical truth. Different minerals expand and contract at different rates when heated and cooled. Granite is a mixture primarily of quartz and feldspar. When you apply intense, localized heat to a granite surface, these components heat up unevenly. The quartz expands faster than the feldspar, creating immense internal stress. The ancient workers would build a hot, controlled fire directly against the rock face they wanted to shape. They might use wood, charcoal, or even dried dung as fuel, banking the fire to concentrate the heat on a specific area. Once the stone was glowing hot, perhaps after many hours, they would rapidly cool it by dashing water or even vinegar against the superheated surface. This sudden thermal shock was the key. The outer layer of rock, now expanded and then violently contracted, could not withstand the strain. It would spall off, flaking away in sharp, thin pieces. This process could be repeated, slowly eating away at the granite, layer by layer, to achieve a desired shape or to create a preliminary groove that could be finished with stone hammers. The evidence for this method is both physical and literary. At many ancient quarry sites, from Cornwall in Britain to the copper mines of the ancient Near East, archaeologists have found rock faces scarred with clear signs of intense, localized heating. The stone appears vitrified, almost glazed in spots, and is often surrounded by layers of charcoal and ash. In some Egyptian contexts, particularly in harder stone quarries, there are depictions and textual references to the use of fire in mining operations. But this method had significant limitations, and understanding them tells us a lot about how these techniques were strategically combined. Fire setting is spectacularly effective for bulk removal, for breaking down large outcrops or creating initial trenches. It is, however, wildly imprecise. You cannot carve delicate hieroglyphs or achieve a mirror polish with a roaring fire. The heat creates microfractures deep into the stone, weakening its overall structure. For the fine work, the final dressing of a block or the intricate details of a sculpture, it was utterly useless, so the picture that emerges is one of a sophisticated, multi-stage operation. Fire setting might be used for the initial, brutal work of quarrying or rough shaping. Then, the wedge and feather method would take over for controlled splitting. Finally, the patient, grain-by-grain abrasion with Dolerite pounders and sand would bring the surface to its final, smooth state. Fire was not a magic wand. It was a crude but powerful preliminary tool, a way to let the fundamental physics of heat and expansion do the heavy lifting, so that human hands and more refined techniques could complete the masterpiece. The granite was now a defined block, but its surface was a chaotic landscape of fractures and ridges. For the final act of creation, for the smooth planes and perfect angles that defined their architecture, ancient craftsmen turned to a tool of breathtaking simplicity and brutal endurance, the Dolerite Pounder. This was not a delicate instrument, but a fist-sized ball of stone, often sourced from riverbeds where water had naturally rounded it into a perfect, hand-fitting shape. Dolerite is an igneous rock even harder than granite, and in the hands of a skilled worker, it became a persistent, unrelenting hammer. The method was as straightforward as it was laborious. A worker would simply strike the granite surface with the pounder, not to break it but to pulverize it. Each blow crushed the microscopic crystals at the point of impact, reducing them to a fine dust and sand. This debris was then swept away, and the process repeated millions upon millions of times to slowly, inexorably wear the stone down. It was a battle fought not with a single decisive strike, but with the accumulated force of countless tiny victories. The evidence for this is etched with stunning clarity into the very monuments we admire. The most powerful classroom for this technique is the Unfinished Obelisk in Aswan. Lying in its granite bed, the obelisk is a fossilized moment of work in progress. Its sides are not smooth, but covered in long, parallel channels that look like giant claw marks. These are the direct result of teams of workers using Dolerite pounders. They would stand in these trenches, swinging their stone hammers in rhythm, gradually deepening the groove that would eventually separate the obelisk from the bedrock. You can almost hear the rhythmic thud of stone on stone, see the dust rising in clouds, feel the blistering heat of the Egyptian sun on their backs. The scale of labor this represents is almost beyond comprehension. To shape just one of these colossal stones required not days or weeks, but likely years of continuous, coordinated effort. It speaks to a society capable of organizing and sustaining specialized labor on a grand scale, of feeding, housing, and motivating hundreds, perhaps thousands, of workers toward a single generational goal. This was not mindless toil, but a highly skilled craft. The angle of each strike, the consistency of the rhythm, the reading of the stone's grain to avoid creating weak points, all of this required deep, tacit knowledge passed from one generation to the next. The Dolerite Pounder, in its crude simplicity, symbolizes the core truth of this entire endeavor. There was no lost technology, no supernatural intervention. The method was persistence, physics, and profound human will, grinding away at the impossible until it finally yielded. Yet even the most patient pounding has its limits, especially when the task calls for a straight, clean cut. For slicing a massive granite block into slabs, or for creating the intricate joints that would lock a temple together, ancient engineers needed something more precise. Their solution was deceptively simple, a tool that transformed one of the hardest substances on Earth into its own undoing. They used a saw, but this was no ordinary metal blade. It was a thin sheet of copper, a soft metal that would have bent against the granite if used alone. The true cutting edge came from something they had in endless supply: sand. The process was a masterclass in applied physics. A worker would draw a straight line on the stone where the cut was needed. Then, using a saw that was little more than a copper sheet without teeth, they would begin a back-and-forth motion. The critical ingredient was an abrasive slurry, a mixture of water and ordinary quartz sand. As the saw was pulled, it would drag the wet sand grains beneath it. Quartz, the same mineral that gives granite its hardness, has a Mohs rating of 7. The copper of the saw, by comparison, is around a 3. So the saw itself was not cutting the stone, it was simply serving as a carrier, pressing the countless tiny, hard quartz particles against the granite surface. Each pull of the saw ground these particles into the stone, scratching and gouging microscopic channels. With enough time and persistence, this abrasive action would wear a groove deeper and deeper, effectively grinding its way through the rock. It was a slow, steady process of erosion, turning the stone's greatest strength against itself. The sand did the cutting, while the soft copper saw was slowly worn away itself, constantly needing to be replaced or resharpened. This method left a distinctive signature that modern archaeologists can recognize. The sides of a cut made with an abrasive saw are not rough or fractured. They are often remarkably smooth, with parallel striations running the length of the groove, the permanent record of each grain of sand's journey. Experimental archaeologists have put this theory to the test with remarkable results. Using replicated copper saws and a slurry of sand and water, researchers have demonstrated that a team of dedicated workers could indeed cut through hard stone like granite and basalt. The cuts are slow, perhaps only a few millimeters per hour, but they are clean, controllable, and entirely achievable with the materials available thousands of years ago. This technique reveals a profound intellectual leap. It shows that these builders understood the principle of relative hardness. They knew they did not need a tool harder than the stone. They just needed a way to deliver a harder substance to the stone's surface. It was a shift from brute force to guided friction, a quiet, grinding persistence that could eventually slice through a mountain. The saw could slice a block, but what if you needed to bore a perfect hole straight through its heart? For that, ancient engineers developed one of their most ingenious and precise tools, the tubular drill. This was not a tool for removal, but for extraction, and the evidence it left behind is a fossilized moment of ancient technology in action. The most famous examples are the drill cores found in Egypt, some still lodged in unfinished work, others left as discarded artifacts. These cores are solid cylinders of granite, basalt, or diorite, perfectly circular and often showing the unmistakable spiral grooves of a cutting tool's path. They are the physical proof of a method so advanced it seems out of place in the ancient world. The tool itself was deceptively simple, a hollow tube made of copper. It had no teeth, no sharpened edge. Like the flat saw, its cutting power came from an abrasive slurry, typically wet quartz sand. The tube would be placed vertically against the stone and rotated, either by a bow drill mechanism for smaller holes or by teams of workers using a capstan-like arrangement for larger ones. As it turned, the copper edge would press the hard sand grains against the granite. The abrasive action would grind away a circular channel, creating a groove that grew deeper with each rotation. Because the drill was hollow, it would leave behind a solid core of untouched stone in its center, which could later be broken free and removed. The spiral grooves on the recovered cores tell a vivid story. They show a consistent, steady feed rate, indicating a controlled and continuous drilling process. The spacing and depth of these grooves even allow modern researchers to estimate the pressure applied and the speed of rotation. This was not haphazard pounding, it was a calibrated operation. But why go to such extraordinary lengths to create a hole? The applications were both practical and profound. On a functional level, tubular drilling was essential for creating precise joints. Imagine fitting a massive stone lintel over two vertical columns. A cylindrical hole drilled partway into the top of each column could accept a stone tenon, a protruding knob on the bottom of the lintel, creating a stable, locked connection that could withstand earthquakes and time. It was also used to create handles or lifting bosses, temporary protrusions left on stones so ropes could be secured for transport, which would later be chiseled off once the block was in place. On a decorative level, this technology enabled the creation of intricate stone vessels, like the famous hardstone vases from pre-dynastic Egypt, with their impossibly thin walls and perfectly symmetrical interiors. The implications of this simple copper tube and some sand are staggering. It demonstrates a complete mastery of rotational motion and abrasive machining. It shows that these builders were not just stone workers, they were early mechanical engineers, understanding concepts of torque, feed pressure, and material wear. The tubular drill transforms our image of their workshops from scenes of brute force to spaces of focused, repetitive precision, filled with the steady, grinding whir of copper on stone and the patient hands guiding a tool that could conquer the hardest rock on Earth. A block of granite freshly separated from the quarry was a far cry from a finished stone. It was a brute, a giant with a rough, fractured hide and uneven dimensions. The next stage, transforming this raw mass into a precisely shaped building block, required a different kind of artistry, one focused on patient reduction and meticulous control. This was the work of dressing and finishing, a process that turned a quarried stone into a piece of a perfect puzzle. The initial rough shaping often began with the same tool used in the quarry, the Dolerite Pounder. Teams of workers would systematically hammer away the most prominent ridges and irregularities, gradually bringing the block closer to its intended form. But pounding alone could not achieve the flat, smooth surfaces needed for a tight joint. For that, they moved to grinding, using hand-sized stones made of an even harder abrasive material, like emery or coarse sandstone. They would rub the granite surface in long, deliberate strokes. This was often combined with an abrasive slurry of sand and water, creating a grinding paste that accelerated the process. It was a slow, methodical sanding on a colossal scale, each pass removing mere grains of stone, yet over time producing a plane of remarkable evenness. The ultimate test of this skill was not in a single stone, but in how multiple stones came together. The evidence here moves from Egypt to the high Andes of Peru to the fortress of Sacsayhuaman. Here, the stonework achieves a level of precision that seems to defy the era. Enormous blocks of irregular, polygonal shapes are fitted together so tightly that the joints between them are virtually invisible. You cannot slide a piece of paper, much less a razor blade, between the stones. The fit is so exact that the contours of one block perfectly mirror the complex, often curved surface of its neighbor. This was not achieved by carving standard rectangular blocks. Instead, it implies a process of iterative fitting. A block would be roughly shaped, then trial fitted against its neighbor. The high spots would be marked, the block lowered, and those spots carefully ground down with abrasives. This cycle of fit, mark, and adjust would be repeated countless times until the two stones locked together as if they were one continuous piece of rock. What does this imply? It speaks to a staggering level of skill, patience, and geometric understanding. The builders were not just cutting to a predetermined plan, they were solving a three-dimensional puzzle in situ with an intuitive grasp of form and space. It suggests the use of precise measuring tools, perhaps simple plumb bobs and water levels, but more importantly, an ingrained standard of craftsmanship where perfection was the only acceptable outcome. The joints at Sacsayhuamon were not just for show, they were a feat of seismic engineering. That intricate, interlocking fit allowed the entire structure to flex and settle during earthquakes without collapsing, a testament to how their pursuit of perfection was rooted in profound practical wisdom. The finished surface, after all this grinding, might then receive a final polish. Using progressively finer abrasives, perhaps even leather pads with powdered rock, workers could bring the granite to a smooth, almost reflective sheen, catching the light and making the stone itself seem to glow. This journey from a ragged quarry block to a luminous, perfectly fitted stone reveals the true heart of their craft, a relentless pursuit of precision hidden within the patient, granular labor of countless hands. Polishing a stone to a perfect finish was a monumental task, but it paled in comparison to the next challenge. You now had a flawless, multi-ton block of granite, and it needed to be moved, often across miles of uneven ground, to its final destination. The first and most fundamental tool for this impossible journey was not a machine, but an idea, a principle of physics so simple a child uses it on a playground. The lever. For the ancient engineer, the lever was the essential first step in convincing a mountain to walk. The principle is beautifully straightforward. A lever is a rigid bar that pivots on a fixed point called a fulcrum. By applying force on one end, you can lift or move a much heavier load on the other end. The mechanical advantage comes from the distances involved. If the distance from the fulcrum to where you apply your force is 10 times longer than the distance from the fulcrum to the load, you effectively multiply your strength tenfold. A single person using a long enough lever could theoretically lift a weight far beyond their own capacity. In practice, moving a megalith required this principle on a heroic scale. The levers would have been massive timbers, likely from strong, resilient trees like cedar or oak. Workers would first need to create a pivot point. They might slide a flat stone or a stack of wooden blocks underneath one edge of the granite block to act as a fulcrum. Then, teams of men would insert the ends of several long timber levers into gaps or under the stone's edge. On the count, they would throw their collective weight downward on the long ends of the levers. With a chorus of grunts and the groaning of wood, the colossal block would tilt ever so slightly, pivoting on that fulcrum. This tiny movement was everything. Once the stone was lifted even a few inches, workers could quickly shove rollers, wooden cribbing, or packed earth underneath it. Then they would reset the levers, find a new fulcrum point, and repeat the process, inching the stone upward or sideways in a slow, rhythmic dance of lift and pack, lift and pack. The limits of this method were as real as its advantages. The mechanical advantage is tremendous, but it is not magic. The timbers themselves had limits. They could splinter or snap under the incredible stress. Each lift only achieved a small displacement, meaning progress was agonizingly slow. For a stone weighing hundreds of tons, you would need an army of levers and an army of men working in perfect, coordinated harmony. This was not a method for speed or distance, but for control. It was the perfect tool for the delicate, precise work of positioning a stone onto its foundation, or for making the fine adjustments needed after a block was dragged into place. The lever did not move the mountain across the valley, but it taught the mountain how to take its first, tentative step. It transformed an immovable object into something that could, with patience and collective effort, be persuaded to shift. This simple tool, a long pole and a pivot point, represents the foundational logic of all that followed, the first whisper of motion in a world of stationary giants. Lifting a stone was one thing, but transporting it across miles of rugged terrain required a different kind of magic, one that transformed sliding friction into rolling motion. The most enduring image of this feat is the classic theory of the wooden roller. Picture a colossal stone block carefully levered up onto a massive wooden sledge. Beneath this sledge, teams of workers lay a track of parallel logs, each one a sturdy, rounded trunk stripped of its branches. The principle is simple yet transformative. Dragging a heavy sledge directly on the ground creates immense friction, a constant, grinding resistance that requires staggering force to overcome. But when that sledge rests on a series of logs that can roll, the friction is drastically reduced. You are no longer dragging the weight, you are coaxing it to roll forward on a constantly renewing path of wooden wheels. The physics here are compelling. Experiments and basic engineering principles suggest that moving a given weight on rollers requires only a fraction of the force needed to drag it on a flat surface. Some estimates suggest the required pulling force could be reduced by as much as 80 or 90%. This is not a trivial difference. It is the difference between an impossible task and a manageable, albeit Herculean, one. So how many people would it actually take? For a stone like the 800-ton blocks of Baalbek, even with rollers, the numbers are sobering. Calculations based on known coefficients of friction suggest it might still require the coordinated pull of several hundred individuals, all harnessed to long, heavy ropes made of woven plant fibers like hemp or papyrus. This was not a chaotic tug of war, but a precisely orchestrated operation, likely directed by rhythmical drumbeats or chants to synchronize the effort, turning individual strain into a single, pulsing force. But the roller method presents one infamous logistical puzzle, often called the roller problem. As the sledge moves forward, the logs at the back are left behind. To continue the journey, these logs must be constantly carried from the rear of the train to the front, placed down ahead of the advancing stone. This creates a cycle of frantic activity, a secondary team of workers racing to keep the wooden track moving faster than the stone itself. It turns a linear pull into a circular, never-ending relay race of heavy timber. Did ancient cultures actually use this method? While no intact roller track has survived the millennia, we have compelling hints. From ancient Egypt, tomb paintings and reliefs from the Old Kingdom show clear scenes of colossal stone statues being transported. In these images, a giant figure is strapped to a sledge, and a team of workers is shown pouring a liquid, likely water or oil, on the ground in front of the runners. This is a critical detail, lubrication to further reduce friction. A man often stands on the knees of the statue, clapping or chanting, presumably to coordinate the pulling teams. In Mesopotamia, cuneiform texts describe the movement of stone monuments, mentioning the use of wooden beams and vast numbers of laborers. These are not technical manuals, but they corroborate the basic elements of the story: sledges, lubricants, and immense human coordination. The roller theory is elegant in its simplicity, but its execution on the scale of the largest megaliths pushes the limits of our imagination. It asks us to envision a scene of orchestrated chaos, a symphony of grunting labor, shouting foremen, and the endless, thunderous roll of logs under the weight of history itself. Rollers solved the problem of friction, but they introduced a new one, a frantic logistical ballet of moving logs from back to front. For truly epic journeys, ancient engineers developed a more permanent and controlled solution: the slipway. This was not a temporary track of rolling logs, but a carefully prepared road, engineered specifically for the single purpose of moving a mountain. The concept was to create a smooth, hard, and often lubricated pathway that could guide a sledge from quarry to construction site with maximum efficiency and minimum chaos. Evidence for such engineered roads exists in tantalizing fragments across the ancient world. On the slopes leading from the famous red granite quarries at Aswan down to the Nile River, archaeologists have identified what appear to be prepared transport ramps. These were not mere dirt paths but reinforced roadways, likely paved with limestone chips or packed clay to create a firm, level surface capable of bearing unimaginable weight. The most iconic use of the slipway, however, is intimately connected to the pyramids themselves. The Great Pyramid of Giza is surrounded by a persistent and compelling theory that massive ceremonial causeways built of stone and lined with polished limestone served a dual purpose. While they provided a sacred processional route for the pharaoh's final journey, their robust construction and direct path from the river valley to the plateau make them perfect candidates for the functional highways that delivered millions of stone blocks. A stone block arriving by barge on the Nile would be transferred to a colossal wooden sledge. This sledge would then be pulled up these immense, paved inclines, a slow, agonizing climb of hundreds of feet, with a gradient carefully calculated to be just manageable for teams of pullers. But even the best paved road creates immense friction under a load of 70 tons. Here, the ancient engineers employed a simple yet brilliant trick: lubrication. Tomb paintings and reliefs from Egypt show a vivid detail: a worker standing before a moving sledge, pouring a liquid from a jar onto the ground directly in front of the wooden runners. This was likely water, which with the desert sand would create a slick slurry of mud, a natural lubricant. Other cultures might have used animal fats or oils. The effect is profound, turning a dry, gritty drag into a slick, almost hydrodynamic glide. Experiments have shown that wetting the surface before a heavy sledge can reduce the required pulling force by half or more. This transforms the labor equation, making the impossible merely arduous. We see a parallel concept on the other side of the world, on Rapa Nui, Easter Island. Researchers studying the transport of the massive Moai statues have long debated the methods. One compelling hypothesis involves the use of prepared roads. Across the island, archaeologists have mapped ancient paths, some worn into the bedrock, that connect the quarry to the various coastal platforms. These are not random trails, they show signs of preparation and were consistent with the repeated movement of heavy, sliding loads. The theory suggests the statues, carved lying on their backs, were somehow rocked and walked upright for short distances, but for longer hauls, they may have been laid on a wooden sledge or cradle and pulled along these lubricated roads. The image is universal, from the deserts of Egypt to the remote Pacific, a symphony of coordinated labor, the scent of wet earth and sweat, the sound of chanting and creaking ropes, and the slow, relentless slide of stone on a path made slick by human ingenuity. The slipway was more than a road, it was a linear machine, a channel for focused will, proving that the journey of 1,000 miles for a megalith began with a single, carefully greased step. The true power of the lever and the slipway could only be harnessed by one thing: a strong rope. This simple technology, twisted from the fibers of plants or strips of animal hide, became the literal lifeline of megalithic construction, the crucial link between human muscle and immovable stone. Without a reliable means to pull, no amount of clever engineering could make a block budge. The materials they used were a testament to their resourcefulness. In Egypt, ropes were famously made from papyrus reeds or the fibers of the date palm. These plants were soaked, pounded, and then twisted into thick, incredibly strong cables, sometimes braided into multiple strands for added durability. In other parts of the world, hemp, flax, or even leather strips served the same vital purpose. These were not delicate twines, they were engineering components, each one capable of withstanding tons of tension. A single rope might be as thick as a man's arm, and for the largest stones, dozens of these ropes would be attached to a single sledge, fanning out like the reins of a colossal chariot. The organizational challenge this created was staggering. Picture a stone like the 800-ton blocks of Baalbek, lashed to its sledge and resting on its lubricated slipway. Attached to it are not 1 or 2 ropes, but perhaps 50, each one 50 yards long. At the end of each rope, a team of 20 pullers takes their position. Suddenly, you are not just moving a stone, you are commanding a small army of 1,000 individuals. The coordination required for this operation defies belief. If one team pulls a fraction of a second before another, if one rope goes slack while others are taut, the entire effort could fail, ropes could snap, or the sledge could veer catastrophically off its track. How did they achieve the perfect unison needed to generate a smooth, continuous pull? The answer likely lies in rhythm and leadership. A master foreman, perhaps standing on the stone itself or on a raised platform, would have been the conductor of this physical symphony. Using a drum, a horn, or simply a powerful, rhythmic chant, he would set the beat. On one count, every puller would lean into their harness, taking up the slack. On the next count, they would dig in their heels and heave with their entire body weight. This synchronized effort transformed 1,000 individual tugs into a single, massive wave of force, a pulse of power that could overcome the inertia of the granite giant. Steering such a behemoth was another problem entirely. For this, they may have employed a system of guide ropes. While most teams pulled straight ahead, 1 or 2 ropes on either side could be used for delicate directional control. A signal from the foreman would tell the left side team to hold fast or pull slightly backward, while the right side team continued heaving, pivoting the sledge on its lubricated track with minute precision. This was logistics elevated to an art form. It required not only strong ropes and strong people, but a hierarchy of overseers, team leaders, and signalers, all communicating flawlessly across a chaotic, dusty landscape of straining bodies and thunderous noise. The movement of a single megalith was therefore a triumph of social organization as much as engineering physics. It proved that humanity's greatest tool was not the lever or the roller, but our ability to unite countless individual wills toward a single, earth-moving purpose. Even with 1,000 pullers on a rope, the final challenge remained vertical. How do you lift an 80-ton block of granite 60 feet into the air to complete a temple wall? The lever could provide a tiny lift, but for sustained elevation, ancient engineers turned the very landscape into a machine. They built ramps. This was the ancient crane, a stationary inclined plane of earth, brick, and rubble that transformed an impossible vertical climb into a long, manageable horizontal pull. The principle is pure physics. Dragging a heavy weight straight up is a fight against gravity itself, requiring a force greater than the object's own weight. But by extending that vertical distance into a long, gentle slope, you trade a short, brutal effort for a long, sustainable one. You reduce the required force at any given moment, spreading the work over time and distance. For a pyramid, the most iconic application, the numbers are staggering. To raise a 2.5-ton block 200 feet using a straight ramp with a gentle 5% grade, you would need a ramp over 3/4 of a mile long. The construction of this temporary mountain to build the permanent one was a project in itself, requiring millions of tons of mud brick, limestone chips, and packed earth. Workers would have maintained this colossal earthen highway, constantly reinforcing its surface as teams of pullers, harnessed to sledges, trudged up its length in a slow, endless procession. The air would have been thick with dust and the smell of sweating laborers and animals, the ground trembling with the cumulative weight of stone and human effort. But the straight ramp theory has a significant flaw, especially for a smooth-sided pyramid. As the structure grows taller, the ramp must grow longer, wider at its base, and consume truly absurd amounts of material. By the final stages, you might be using more material to build the ramp than the pyramid itself. This has led to proposed variations like the spiral ramp. This model suggests a ramp winding around the outside of the rising pyramid, like a mountain road. It would be shorter in total length than a straight ramp and could reuse material from the lower sections as the work progressed upward. However, it presents its own severe difficulties. A ramp tight against the pyramid's face would obscure the builder's view of the structure's precise geometry, making it incredibly hard to maintain the perfect alignment the pyramids are famous for. The corners of the pyramid would also become major obstacles, requiring complex engineering to navigate sledges around them. Each model, the straight-on assault and the encircling spiral, represents a different calculation in the ancient ledger of labor and logistics. The straight ramp demands more material, the spiral ramp demands more precision and creates more points of potential failure. Some researchers even propose a combination, a massive straight ramp for the lower, bulk stages of construction, switching to a shorter spiral or a series of internal ramps within the pyramid's own core for the final precision work at the apex. What all these theories underscore is that the ramp was never a single, static tool. It was a dynamic, evolving piece of infrastructure, constantly redesigned and rebuilt in response to the growing monument before it. The ramp was the ultimate expression of patient, incremental progress, a testament to the idea that any height can be reached if you are willing to build a long enough and strong enough path to walk there. The ramp was a triumph of landscape engineering, but it demanded immense space and material. For more confined spaces or for the final, delicate act of positioning a stone onto its precise foundation, ancient builders may have turned to a more elegant and dynamic tool, one borrowed directly from the lifeblood of their agriculture. Along the banks of the Nile for thousands of years, farmers used a simple device to lift water from the river to their fields, the shaduff. This was a counterweighted lever, a long pole balanced on a crossbeam with a bucket on one end and a heavy lump of mud or stone on the other. The farmer would pull the bucket down into the water, and the counterweight would make lifting it full of water almost effortless. Now, envision this principle scaled up to a monumental level. A massive timber beam, perhaps the trunk of a great cedar, is mounted on a sturdy wooden frame. On one end of this beam, a strong rope or a set of ropes is attached, secured to the end of a granite block. On the other end, a huge basket or net is filled with stones, acting as the counterweight. The genius of this system is its incremental control. Workers would pull down on the rope end, leveraging the counterweight to lift the stone just a few inches. Immediately, other workers would slide wooden cribbing, a stack of timber blocks, underneath the raised edge. The tension is then slowly released, and the stone comes to rest securely on this new, slightly higher platform. The counterweight is then adjusted, perhaps by adding more stones to the basket, and the process is repeated on the opposite side or a different corner. In this slow, rocking dance, the stone is walked upward, inch by precious inch, in a controlled, stable manner. This method solves several critical problems at once. It requires far less brute manpower than a direct pull, as the counterweight does most of the work. It offers exceptional precision, allowing for micro-adjustments impossible with a ramp and sledge. And it is relatively compact, needing only a clear space above the stone rather than a massive earthen incline. While direct archaeological evidence for such a megalithic shaduff is scarce, the principle is undeniably present in their technological world. We know they understood counterweights and levers intimately. The simple shaduff was ubiquitous in their daily life, a tool every engineer would have grown up with. Scaling a familiar, trusted technology to solve an unprecedented problem is a hallmark of human ingenuity. It transforms a tool for sustaining life into a tool for creating legacy, using the balanced logic of the riverbank to lift the foundations of eternity. But what if the most powerful tool for moving these giants wasn't wood or rope, but water itself? The Nile River was Egypt's highway, and it makes intuitive sense that a civilization that thrived along its banks would use its annual gift to their advantage. The theory of floating megaliths proposes a breathtakingly elegant solution. Instead of dragging a 1,000-ton obelisk for miles across the desert, you could simply wait for the floodwaters to rise, guide the stone onto a massive barge, and let the river carry it to its destination. The logic is compelling. Water buoyancy neutralizes weight. A stone that would crush any land-based transport system becomes manageable when cradled by a carefully designed boat. The challenge then shifts from brute force to naval architecture and precise timing. Could ancient shipwrights build vessels strong enough for such a task? We have tantalizing clues. From the pyramid complex of Pharaoh Khufu at Giza, archaeologists discovered the remains of a magnificent ceremonial ship, over 140 feet long, built with intricate interlocking planks. While not a heavy transport barge, it demonstrates a sophisticated understanding of large-scale wooden shipbuilding. More direct evidence might lie in the quarries themselves. At Aswan, the granite quarries are situated right on the east bank of the Nile. When the annual inundation occurred, the river would swell, its waters rising up to and into the quarry basins. It is entirely plausible that engineers timed the final extraction of a block to coincide with this high water, allowing them to maneuver it directly from its quarry bed onto a waiting, buoyant cradle. The block would then be secured, and as the floods receded, the now laden barge would float free, ready for its downriver journey. This method wouldn't just apply to Egypt. For the massive stones at Baalbek, researchers have noted the presence of ancient, dry riverbeds and evidence of sophisticated Roman-era water management nearby. Could a temporary canal have been dug from the quarry to a nearby watercourse, creating a liquid slipway for the final leg of the journey? The concept transforms the landscape from an obstacle into a partner, using seasonal rhythms and hydraulic engineering to turn Earth's most abundant liquid into a cosmic conveyor belt. The evidence is circumstantial but powerfully suggestive. It asks us to see these builders not just as masters of stone, but as partners with the very elements, waiting for the river to rise so they could set their mountains adrift. The theory of floating stones offers an elegant solution, but on the remote island of Rapa Nui, the challenge was different. Here, the giant Moai statues had to travel across rugged, volcanic hills from quarry to coast without the benefit of a mighty river. For decades, the leading theory involved dragging them horizontally on sledges or log rollers. Then, a radical new idea emerged, one that suggested the islanders made their statues walk. This theory was not born in a dusty library, but on the grassy slopes of the island itself, through the powerful tool of experimental archaeology. Researchers Terry Hunt and Carl Lipo proposed a method as simple as it was astonishing. They suggested the massive statues, which average around 13 feet tall and weigh 14 tons, were not dragged at all. Instead, they were transported upright, rocked from side to side by teams using ropes, making them appear to walk across the landscape. To test this, they didn't just run calculations, they built a concrete replica of a Moai and tried it. The results were captivating. With 3 teams controlling ropes, one on each side to rock the statue and one behind to steady it, they found a small crew could indeed maneuver the heavy figure with a shuffling, swaying gait. The method was surprisingly energy efficient. By using the statue's own center of gravity and momentum, the teams were not lifting the full weight with each movement. They were simply pivoting it on one corner, then the other, inching it forward. This rocking motion meant the statue spent most of its time resting on its base, drastically reducing the ground pressure and friction compared to dragging a sledge, which could dig into the soft earth. The visual is unforgettable, a towering stone giant seeming to stride purposefully across its homeland, guided by the rhythmic pull of its creators. The efficiency argument is compelling, potentially requiring far fewer people than a massive dragging operation, a critical advantage on an isolated island with limited resources. But every method leaves a signature, and the walking theory predicts a very specific one. If you are rocking a multi-ton statue from side to side as it moves forward, the base is not sliding. It is striking the ground with significant force on alternating corners. This repeated impact, especially on soft ground, should create a distinctive pattern of broken, pitted earth and perhaps even shattered stone along the transport path. Proponents of the theory point to the ancient roads on the island, noting that some show evidence of centralized wear that could align with this kind of motion, rather than the parallel ruts expected from sledges or rollers. However, the method is not without its serious critics and drawbacks. The primary concern is control and risk. A 14-ton statue rocking on a narrow base is inherently unstable. One mistimed pull, one patch of slippery ground, and the giant could topple, potentially shattering on impact and certainly requiring a monumental recovery effort. The many fallen moai found along the island's roads have long been cited as evidence of transport failures, and the walking method, while dynamic, might make such catastrophic falls more likely than a slower, more controlled drag. Furthermore, the largest moai, like the 270-ton El Gigant still in the quarry, would be nearly impossible to balance in this way, suggesting that if walking was used, it had strict upper weight limits. The debate continues because the archaeological evidence remains open to interpretation. The experimental walk proved it was physically possible, but whether it was the method actually used by the Rapa Nui people centuries ago is a different question. It reminds us that sometimes the most elegant solution in a modern experiment might not mirror the practical, risk-averse choices of an ancient culture. Yet the walking moai theory stands as a brilliant example of how hands-on experimentation can shatter long-held assumptions and offer a glimpse of the past that is not just logical, but alive with motion. The sheer audacity of the task at Baalbek forces us to think in terms of a coordinated symphony of methods. Here, the geography itself presents a brutal puzzle. The quarry where the 800-ton Trilithon blocks were cut lies roughly half a mile from the temple platform, but it is not a simple flat haul. The site is on a slight uphill incline, a fact that transforms the physics of the move completely. Dragging such a mass downhill is one thing, gravity can assist. Pulling it uphill, even on the best lubricated slipway, multiplies the required force exponentially. This single detail rules out any single, simple solution. It demands a staged approach, a master plan that combined every trick in the ancient engineer's book. First, the block would have been extracted and dressed in the quarry using the methods we have discussed: the patient pounding, the precise drilling for levers, the careful splitting. Then, the journey likely began with the most reliable tool for horizontal movement, the massive sledge and roller system. A timber cradle of incredible strength would have been constructed beneath the stone. To overcome the initial inertia of 800 tons, the number of pullers would have been staggering, likely in the high hundreds, all synchronized by rhythmic command. They would have inched the block onto a prepared transport road, a Roman-engineered slipway paved with hard-packed gravel and stone chips, designed to distribute the weight and provide a firm, level track. Lubrication, perhaps water or olive oil, would have been constantly applied ahead of the wooden runners to reduce friction to its absolute minimum, but the uphill grade changes everything. Here, the simple rope and pulley, or the Roman treadwheel crane known as a polyspaston, might have entered the equation. While such cranes were typically used for lifting, their mechanical advantage could have been adapted for pulling. Imagine a massive capstan, a horizontal winch turned by teams of men or even oxen walking in a circle, anchored firmly ahead on the path. Heavy ropes from the sledge would be wound around this drum. With each rotation, the capstan would take up the slack, providing a steady, mechanical pull that could be sustained far longer than a direct human tug of war. The uphill climb would have been a series of these staged pulls, moving the stone a short distance, then resetting the anchor points and winches for the next segment. The final act, lifting these giants over 20 feet onto the temple platform, presents the ultimate challenge. A massive earthen ramp built against the platform's side is the most plausible solution. The stone, still on its sledge, would be pulled up this temporary mountain of packed earth and rubble, a final, agonizing climb requiring every ounce of coordinated force. Once at the correct height, levers and possibly a system of counterweights would have been used for the delicate, precise work of sliding it off the sledge and onto its permanent resting place. The precision of the fit, where the joints are virtually invisible, tells us the final positioning was a matter of millimeter adjustments, likely achieved with small levers and stone shims. The Baalbek Trilithon does not point to a single lost technology, but to the peak of known ancient engineering, orchestrated on an unimaginable scale. It represents the culmination of all the principles we have explored, applied with Roman logistical genius and a workforce capable of turning a slow, grinding process into a breathtaking architectural reality. Centuries after Baalbek, a single man in 20th century Florida presented the world with a new megalithic mystery. Edward Leedskalnin, a Latvian immigrant, spent nearly 3 decades from the 1920s to the 1950s working alone at night, constructing what he called the Coral Castle. Using hand tools, he quarried, carved, and positioned over 1,100 tons of oolitic limestone into massive gates, obelisks, and furniture, including a 9-ton revolving gate so perfectly balanced a child could push it. He claimed to have rediscovered the building secrets of the ancient pyramids, speaking of understanding the laws of weight and leverage and harnessing the forces of magnetism. His solitary, secretive work, coupled with his vague references to anti-gravity and the secrets of the Egyptians, has made his site a pilgrimage for those who believe the ancients possessed a lost, perhaps even supernatural, technology that we have since forgotten. Leedskalnin's story is compelling precisely because it mirrors the ancient puzzle so closely, a lone figure achieving what should require an army, all while hinting at a hidden key. While the stone he used was coral rock, far softer and easier to work than granite, the scale of his accomplishment and the shroud of mystery he cultivated force a question. If one man in the modern era, with no formal engineering training, could move multi-ton blocks using only simple tools and clever mechanics, does that strengthen or weaken the case for extraordinary ancient methods? Leedskalnin's actual tools, discovered after his passing, were decidedly ordinary tripods, chain hoists, block and tackle systems, and simple metal levers. His genius appears to have been in the meticulous application of basic physics, patience, and an intuitive grasp of pivot points and counterweights, much like the ancient builders we have been discussing. Yet, because he worked in isolation and offered cryptic explanations, his story has become a modern vessel for the same type of speculation that surrounds the pyramids or Stonehenge. It acts as a powerful bridge, connecting the tangible, tool-based explanations we have explored with the enduring human fascination for a single, elegant secret, a lost knowledge that could make the impossible simple. This fascination is where our exploration must turn next, to the realm of speculative theories, to ask what, if anything, might truly have been lost to time. Leedskalnin's solitary work feeds directly into a much larger modern narrative, the idea of a lost ancient high technology. This concept suggests that our ancestors possessed advanced knowledge or tools far beyond simple levers and ramps, a sophisticated science that was somehow erased by time. Proponents of this view point to the same impossibly precise cuts, the mind-bending scale, and the logistical nightmares we have been exploring. They argue that conventional explanations, while plausible for smaller works, cannot fully account for the most extreme examples. Instead, they propose alternatives that range from the ingenious to the otherworldly. Some suggest the use of advanced machinery, perhaps powered by forgotten energy sources, that could slice granite like butter. Others theorize about the application of sound-specific resonant frequencies that could temporarily soften stone or even levitate massive blocks, reducing their effective weight to nothing. The most dramatic proposals look beyond our world entirely, suggesting that such achievements required knowledge or assistance from extraterrestrial visitors. These theories are compelling not because of their evidence, but because of the powerful human desire they tap into, the longing for an elegant, singular secret that unlocks all the mysteries at once. The appeal is undeniable. It transforms the patient, granular labor of thousands into a moment of magical efficiency. It replaces the image of sweating workers and splintering timbers with one of enlightened masters wielding devices of clean, effortless power. This narrative offers a satisfying answer to the visceral question of how, an answer that feels proportionate to the staggering scale of the monuments themselves. Who would not want to believe that humanity once possessed, and perhaps could regain, such a graceful command over the physical world? Yet when we search for the foundation of these ideas, we encounter a profound silence in the archaeological record. There is no workshop uncovered with strange, unrecognizable tools. No ancient text or illustration depicts a device for sonic levitation or a power source beyond human or animal muscle. The rubble heaps beside every ancient quarry are not filled with mysterious machinery, but with countless broken stone hammers, worn copper saws, and the debris of trial and error. The evidence that does exist consistently points toward the incremental, the laborious, and the brilliantly simple. This brings us to a fundamental principle of reasoning often applied in such debates: Occam's razor. This is not a tool for cutting stone, but for cutting through speculation. It suggests that among competing explanations, the one that requires the fewest new assumptions is usually correct. In this case, we have two sets of ideas. One set relies solely on materials and physics we know the ancients possessed, demonstrated through tool marks, experiments, and historical accounts. It requires no new inventions, only the sophisticated application of known principles on a staggering scale. The other set introduces entirely new categories of technology for which we have no direct proof, only the absence of a complete conventional explanation. The razor asks us which path is more straightforward. Does the precision of a stone joint truly demand a laser? Or can it be achieved through a lifetime of skill with a string, a plumb bob, and an abrasive cord? Does moving an 800-ton block require anti-gravity, or does it simply require the coordinated will of 1,000 people on a greased track for a very, very long time? The choice is between a world where miracles are commonplace and a world where human patience and ingenuity are themselves the miracle. This is not to dismiss the mystery or to claim we have every answer. The exact configuration of the ramp at Giza, the precise method for the Moai walk, the full logistics of Baalbek, these details remain open for debate and discovery. The true high technology of the ancients may not have been a device, but a social technology, an unparalleled ability to organize, motivate, and sustain vast projects across generations. Their genius was in seeing potential in the mundane: a crane in a lever, a conveyor belt in a river, a precision machine in a length of twine and some sand. To reduce their achievement to a lost gadget is, in a way, to diminish it. It takes more wonder, not less, to believe that people just like us, with hands and minds and relentless determination, moved mountains using nothing but the world around them and the ideas within them. The stones stand not as proof of a forgotten power source, but as monuments to the most powerful force of all, the collective human spirit applied with unwavering focus over time. And that leads to a final, haunting possibility. What if the greatest secret they possessed is one we have never lost, but have simply forgotten how to use on such a scale? The most sophisticated device in their entire toolkit was not made of wood or stone, but of people. For all our focus on levers and ramps, the true engine behind these projects was social organization, the ability to marshal, direct, and sustain human effort on a scale that still feels monumental. Without this invisible architecture of labor, the physical architecture would have been impossible. This was the ultimate social engineering, turning the collective strength of a civilization into a single, earth-moving force. Ancient states mastered this through several powerful systems. One of the most common was the corvée system, a form of labor tax. During the agricultural off-season, when the fields were flooded or lay fallow, farmers would be called upon by the state to contribute their labor to public works projects. This was not necessarily a life of hardship, but a civic duty, a way to pay one's dues to the pharaoh or the community while also receiving food, shelter, and a sense of shared purpose. It transformed idle time into productive, nation-building effort, creating a rotating, renewable workforce of thousands. For other cultures, the motivation was deeply spiritual. The construction of a temple or a sacred monument was an act of devotion, a direct service to the gods that promised divine favor for the entire community. This religious fervor could inspire voluntary labor of incredible dedication and precision, where the act of building was as important as the finished structure. The work itself became a form of worship, a prayer made physical. This changes how we view so-called brute force methods. Dragging an 800-ton block with 1,000 pullers does not seem so impossible when you realize that the state had the administrative machinery to recruit, feed, and coordinate those 1,000 individuals as a single unit. It was a matter of logistics, not just muscle. Scribes would keep meticulous records of workers, their shifts, and their rations of bread, beer, and fish. Overseers with decades of experience would manage the complex ballet of teams, ensuring that when the drumbeat sounded, every rope tightened in unison. This level of organization turned a chaotic mob into a precision instrument. The pyramid builders' camps discovered at Giza are a testament to this. These were not squalid slave quarters, but structured communities with bakeries, breweries, infirmaries, and housing for skilled workers. They reveal a society that invested in its labor force, understanding that a well-fed, cared-for worker was a more effective and stable one. The real innovation, then, may have been in management, in the development of a bureaucracy capable of planning projects that spanned decades or even generations. This long-term vision allowed for methods that seem agonizingly slow to us. If a project is expected to take 20 years, then moving just one massive stone per year is not a failure of technology, it is part of the plan. The patient, granular work of pounding granite with stone hammers or grinding joints with sand becomes feasible when you have a dedicated guild of craftsmen passing their skills from father to son, each generation adding a few more inches to the rising wall. This perspective reframes the entire mystery. We have been searching for a lost machine that could cut and lift stone, but perhaps the machine was always there, walking on two legs, singing work songs to keep the rhythm, and finding meaning in a shared endeavor greater than any single life. The true lever that moved the world was not a length of timber, but the collective will of a culture, meticulously organized and relentlessly focused on a goal that would outlast them all. This invisible architecture of labor depended on something even more fragile than rope or timber, knowledge. How does a society preserve the precise techniques for moving an 800-ton block across centuries without a single engineering textbook or detailed blueprint to guide them? The answer lies not in libraries but in living tradition, in the slow, patient transfer of skill from one pair of hands to another. This was a world of apprenticeship where a young boy would join a work site not to read plans but to watch, to listen, and to feel the work in his own muscles. He would begin with the simplest tasks, perhaps hauling sand for the abrasive slurry or fetching water for the pullers. For years, he would absorb the rhythm of the site, the cadence of the work songs, the subtle gestures a master used to check a stone's level with nothing more than a length of wet string. The knowledge was not a list of steps but a sensory wisdom, an intuition for the material. He would learn the sound granite makes when a wedge is placed correctly, a subtle change in pitch before the crack. He would come to recognize the feel of a Dolerite Pounder when its edge was wearing thin, and know exactly how to dress it on another stone. This was a holistic education where the physics of leverage was understood not as an equation, but as the strain in your back when a timber was too short and the relief when a longer one was found. The master craftsman was a repository of generations of trial and error, of solutions to problems that only arose once in a lifetime. How do you free a sledge when it sinks into unexpectedly soft ground? What mixture of sand and water cuts fastest on a particularly dense vein of quartz? These were solutions passed down in stories and demonstrations, often wrapped in the language of ritual or myth to ensure they were remembered with reverence. The construction of a temple was not just a technical project, it was a cultural ceremony, and the methods were sacred lore. This oral and practical tradition created a profound conservatism in technique. Why change a method that you know works, that your grandfather's grandfather used to raise the great columns? Innovation happened, but it was glacial, the product of accumulated minor improvements over centuries, not sudden invention. A slightly better way to braid a rope, a new quarrying trick discovered by accident. These small advances would be incorporated into the tradition and passed on. This system was incredibly robust for maintaining continuity, but it was also vulnerable. A single generation of disruption through war, famine, or social collapse could sever that chain of transmission forever. The specific tricks for moving the largest stones, the nuanced understandings that were never written down, could vanish into the air, leaving only the silent, impossible stones themselves as a testament to a knowledge that was once as common as the calloused hands that wielded it. Theories are compelling, but the only way to truly test them is to get your hands dirty. This is the realm of experimental archaeology, where modern researchers put down their books and pick up the tools of the ancients, attempting to recreate their feats to see what actually works. These are not thought experiments, they are physical trials, often grueling and humbling, that separate plausible ideas from practical reality. One of the most ambitious modern efforts took place in the 1990s, led by a team including Egyptologist Mark Lehner and stonemason Roger Hopkins, documented for the Nova television series. Their goal was not to build a pyramid but to answer fundamental questions. Could a small team using only ancient tools and methods quarry, shape, and move a 35-ton obelisk? The project began in an Aswan granite quarry, where they attempted to replicate the extraction of an obelisk using nothing but Dolerite Pounders. The results were immediate and instructive. The stone hammers worked, but the pace was agonizingly slow. A team of about 24 workers, swinging 12-pound pounders in shifts, managed to carve a trench only a few inches deep after weeks of exhausting labor. The sheer physical toll was staggering, revealing that such work required not just skill, but an entire social system to support and rotate a massive, specialized workforce. The real revelation came when they tried to move their smaller 10-ton block. They constructed a massive wooden sledge and placed it on a track of wooden rollers. With a team of about 130 pullers on ropes, they found they could indeed get the block moving. However, they quickly encountered the infamous roller problem in real time. The logs at the back constantly had to be rushed to the front, creating a chaotic, inefficient cycle. More critically, the immense weight of the stone began to crush the rollers, embedding them into the soft desert sand and creating immense resistance. Their solution, one hinted at in ancient art, was lubrication. By pouring water on the sand in front of the sledge, they created a slick slurry of mud. The effect was transformative. The sledge glided forward with dramatically less effort, proving the practical genius of the simple act shown in those Egyptian tomb paintings. This experiment did not prove exactly how the ancients did it, but it proved something more important, that the core principles we have discussed are fundamentally sound. The tools work, the physics holds up, and the methods are achievable with enough coordinated human labor. It confirmed there is no need to invent unknown technologies. The known ones, applied with relentless persistence, are sufficient. Yet the experiment also laid bare the monumental scale of the organization required. Moving their relatively small block required feeding, housing, and directing over 100 people. Scaling that up to a 2.5-ton pyramid block, let alone an 800-ton monolith, multiplies the challenge exponentially, not in kind but in sheer logistical magnitude. It shifts the mystery from how they cut the stone to how they orchestrated the society that made it possible. The stone itself holds the final testimony, a permanent record etched not in papyrus but in granite. To understand how these monuments were built, we must learn to read their surfaces like a forensic investigator, deciphering the unique signatures left by each tool and technique. Every mark tells a story of force and friction, a frozen moment of ancient labor. The most common and brutal signature is pitting. This is the calling card of the Dolerite Pounder. Look at the sides of the Unfinished Obelisk in Aswan or the quarry walls at Baalbek. The surface is not smooth but covered in a chaotic, dimpled texture like the skin of an orange. Each small depression is the result of a single, powerful blow from a stone hammer, crushing the crystals at the point of impact into dust. When you see this pitted surface, you are looking at the slow, granular work of reduction, the patient removal of stone measured in mere grains per swing. It speaks of immense time and coordinated, rhythmic effort. A different story is told by long, straight, parallel grooves. These are the marks of the abrasive saw. Imagine a flat slab of granite with a clean, linear cut. If you look closely at the sides of that cut, you will often see fine, straight striations running along its length. These parallel lines are the permanent tracks left by individual grains of quartz sand as they were dragged back and forth by the copper blade. They indicate a controlled, grinding motion, a method of slicing through stone not by breaking it, but by wearing it away with countless microscopic scratches. This signature points to precision and patience of a different kind, a steady, sawing rhythm rather than a pounding cadence. Then there is the signature of the drill, one of the most elegant and telling of all. When a tubular drill was used, it left behind two pieces of evidence. First, the hole itself, a perfectly circular channel. But more revealing is the core, the solid cylinder of stone left in the drill's center. If you examine such a core, you will often see a beautiful spiral groove running around its length, like the thread of a screw. This groove is the path of a single, stubborn quartz grain that got trapped between the copper tube and the stone, making one continuous, descending cut as the drill rotated. This spiral is the ghost of the tool's motion, a direct record of its rotation speed, feed pressure, and the consistency of the abrasive slurry. It is proof of a sustained mechanical process, not a haphazard one. Even fire leaves its ghost. On quarry faces where fire setting was used, the stone can appear glazed or vitrified, as if lightly melted. The surface might be crazed with a network of tiny cracks from the thermal shock, and the surrounding area is often stained with layers of ancient charcoal and ash. Reading these signatures allows us to reconstruct the workflow. A single block might show pitting on its rough outer faces from initial shaping, straight saw marks on a cut edge, and the beautiful spiral on a drilled lifting hole. By mapping these marks, archaeologists can reverse engineer the construction site, understanding not just what was done, but in what order and with what tools. The stone does not lie. It bears the honest scars of the methods available, a permanent ledger of human ingenuity written in the very language of the earth. These tool marks are a powerful testimony, but they are not a complete instruction manual. For all the evidence we have gathered, from the pitted quarries to the experimental reconstructions, significant gaps in our understanding remain. We can confidently reconstruct the basic principles, the physics of levers and the abrasion of sand, but the precise choreography of these methods on the grandest scale often eludes us. Some aspects of ancient engineering are well supported by direct evidence, like the use of Dolerite pounders or the wedge and feather technique. These leave unmistakable signatures in the stone itself. Others are strong, educated guesses, logical extrapolations from known tools and basic physics, like the use of massive sledges on lubricated slipways. The evidence here is more circumstantial, supported by tomb paintings, logistical calculations, and successful modern experiments. Yet there are details that remain genuinely puzzling, the fine points of execution that would have been second nature to a master builder but are lost to us. How exactly was the pulling force of 1,000 individuals transmitted through ropes without causing catastrophic tangles or snaps? What was the precise mixture of water and sand that yielded the fastest cut for a given type of granite? How did a foreman, without modern surveying tools, ensure that a ramp's gradient remained perfectly consistent over a distance of half a mile? These are the nuances that vanish when a tradition ends, the tacit knowledge that dies with the last apprentice. This uncertainty is not a failure of archaeology. It is a reminder of the complexity we are dealing with. It is unlikely that any single universal method existed. Ancient engineering was not a secret formula, but a vast and adaptable toolkit. The choice of technique would have been a practical decision based on a matrix of local conditions. What materials were available? A culture surrounded by dense forests would rely heavily on timber for rollers and sledges, while a civilization on a treeless island would have to innovate with ropes and rocking motions. What was the scale of the project? Moving a 2-ton block for a house foundation required a completely different approach than launching a 1,000-ton obelisk. And perhaps most importantly, what was the tradition? Builders inherited methods from their teachers, refining techniques that were proven within their specific cultural and environmental context. The solution at Baalbek would have looked different from the solution at Giza, not because one was more advanced, but because they were solving different problems with different resources and different inherited wisdoms. The true picture is one of brilliant, localized adaptation, a human response to the ultimate challenge of stone, shaped by the very earth it sought to conquer. The silent stones do not just ask how they were moved, but why. The staggering investment of time, labor, and life required for these projects demands a motivation beyond mere utility or vanity. It was a force powerful enough to convince generations to devote their lives to moving mountains. That force was belief, woven into the very fabric of their understanding of the universe. For the pharaohs of Egypt, the purpose was divine kingship and cosmic order. The pyramid was not a tomb in the simple sense of a resting place. It was a machine for resurrection, a ramp to the stars. By constructing a perfect, indestructible mountain of stone aligned with the cardinal points and the circumpolar stars, the pharaoh was ensuring his eternal journey to join the gods. This was not a personal monument, but a crucial act of maintaining Maat, the fundamental order of the cosmos. The stability of the state, the annual flooding of the Nile, the cycle of the seasons, all were believed to depend on the pharaoh's successful transition to the afterlife. Therefore, every citizen who hauled a block was participating in a sacred duty that secured the survival and prosperity of the entire kingdom. Their labor was an act of piety, a direct service to the god-king who was the linchpin between humanity and the divine. On the windswept plateau of Rapa Nui, the motivation took a different form: ancestor worship. The massive Moai statues are not deities but deified ancestors. Each one, with its unique features, represented a specific lineage chief or important figure. By carving and erecting these giants on coastal platforms called ahu, the living community believed they were harnessing the supernatural power or mana of those ancestors. The statues facing inland were not sentinels gazing out to sea, but watchful protectors, their backs to the ocean, their stone eyes overseeing and blessing the villages and farmlands of their descendants. The immense effort of quarrying, transporting, and raising a moai was therefore an investment in the community's future. It was a way to ensure fertility for the crops, abundance in the fishing grounds, and protection from misfortune. The work itself was likely imbued with ritual, a communal act that strengthened social bonds and affirmed identity. In the Andes, the motivation intertwined with astronomy and sacred geography. The impossibly precise stonework of sites like Sacsayhuaman or Machu Picchu was not just an engineering flex, it was a way to harmonize human construction with the natural and celestial world. Stones were shaped to mirror mountain peaks, walls were aligned with solstice sunrises, and temples were positioned to capture the light of specific stars. The effort to fit multi-ton blocks so perfectly was an act of reverence, a belief that by creating a seamless bond between the crafted stone and the living rock of the earth, they were tapping into the earth's own power and stability. This context transforms our understanding of the labor. A worker patiently grinding a granite joint for months was not just smoothing a surface, he was performing a meticulous act of alignment, ensuring the entire structure resonated correctly with the forces of the universe. This profound spiritual and cultural context answers the most human question of all: why would they do it? The modern mind, accustomed to hourly wages and quarterly profits, struggles to comprehend a lifetime spent on a single project. But when that project is the literal foundation of cosmic order, the conduit for ancestral blessing, or the anchor connecting heaven and earth, the calculus changes. The work became a form of worship, a path to honor, and a guaranteed legacy. It granted meaning to the grueling effort, turning the quarryman, the rope puller, and the stone dresser from anonymous laborers into essential participants in a story much larger than themselves. Their names are lost, but their shared belief is what truly moved the stones, providing the unwavering will that made the impossible engineering possible. The impulse to move mountains in stone was not confined to one river valley or one island. Across the globe, separated by vast oceans and millennia, human cultures arrived at the same monumental ambition, and their solutions form a fascinating comparative study in ingenuity. Consider the great stone circles of Stonehenge on the Salisbury Plain. While the massive outer sarsen stones were sourced locally, the smaller inner blue stones tell a story of a different kind of journey. These distinctive spotted dolerite stones were quarried from the Preseli Hills in Wales, over 150 miles away. The builders of Stonehenge did not need to cut these pillars from solid bedrock, as they were already naturally formed columns. Their challenge was one of pure logistics, transporting dozens of these multi-ton stones across a landscape of hills, rivers, and forests. While the exact method remains debated, the most plausible theories involve a combination of wooden sledges, rollers, and perhaps even a final leg by water, floating the stones on rafts along rivers and the southern coast of Britain. It demonstrates that the fundamental toolkit of levers, rollers, and ropes was a universal starting point, adaptable to the materials and geography at hand. Far across the Atlantic, in the humid lowlands of ancient Mexico, the Olmec civilization carved a different kind of giant. The colossal heads, some weighing over 20 tons, are sculpted from single blocks of basalt, a volcanic stone even harder than granite. The quarries were in the Tuxtla Mountains, and the finished heads were transported over 60 miles through swampy terrain to their ceremonial centers. How did they manage this? The Olmec likely used the abundant local resources, constructing massive rafts to float the stones down rivers during the rainy season, then employing teams of laborers with ropes and rollers to haul them the final distance overland. The similarity in approach to the Egyptians is striking, not because of contact, but because water and wood presented the same logical solution to the same physical problem. Yet the Olmec innovation was in the artistry, transforming a brute block into a powerfully expressive human face with nothing but stone tools, proving that the challenge of moving stone was only a prelude to the challenge of giving it a soul. Perhaps the most breathtaking parallel in precision comes from the Andes, with the polygonal walls of sites like Sacsayhuaman and Ollantaytambo. Here, the Inca and their predecessors achieved a stone fitting so precise it seems to defy the very concept of separate blocks. Unlike the rectangular blocks of Egypt, these stones are irregular polygons, often with 12 or more sides, each one custom carved to interlock perfectly with its neighbors. The method here likely emphasized a patient, iterative process of trial fitting. A block would be roughly shaped, hoisted into place against its neighbor, and the contact points marked. It would then be lowered, and those high spots painstakingly ground down with stone hammers and abrasive sand, over and over, until the fit was seamless. This technique required no mortar, and its genius was seismic, the interlocking joints allowing the walls to sway and settle during earthquakes without collapsing. It represents a different philosophical approach, one less concerned with moving the single largest stone, and more focused on achieving an unbreakable bond between stones of manageable size, creating a fabric of rock that was greater than the sum of its parts. From the riverine networks of Egypt and Mesoamerica to the rolling hills of Britain and the earthquake-prone mountains of Peru, we see a pattern. The core physics of leverage, lubrication, and abrasion were discovered independently, again and again. There was no global blueprint, only a shared human confrontation with mass and gravity. The differences in their final forms, the clean lines of an obelisk, the rounded mass of a Moai, the intricate puzzle of an Inca wall, speak to their unique cultural visions. But the foundational struggle, the patient, granular work of convincing stone to move and then to fit, binds these disparate builders across time. They each looked at a mountain and saw not an obstacle, but a conversation, one conducted with levers, water, sand, and an unwavering collective will. This global chorus of achievement suggests that the lost knowledge we search for was never a single secret, but a fundamental human capacity, an innate engineering intuition that emerges whenever a culture turns its gaze toward eternity. But this global conversation with stone did not last forever. The great quarries eventually fell silent, the slipways crumbled into dust, and the masterful techniques for moving mountains faded from living memory. How could such hard-won, sophisticated knowledge simply vanish? The answer lies not in a single cataclysm, but in a slow, quiet erosion of the very conditions that made the knowledge necessary. When a civilization stops building on a colossal scale, the intricate, specialized skills required for that scale have no reason to be maintained. Imagine a guild of rope makers whose entire craft is dedicated to weaving cables thick enough to pull an 800-ton block. If the state commissions no more such blocks for a century, why would a father teach his son that specific, arduous skill? The knowledge degrades, replaced by techniques for smaller, more practical tasks. The collapse of the centralized states that orchestrated these projects was often the first blow. The old kingdom of Egypt, the pyramid builders, eventually gave way to periods of fragmentation and instability. When the pharaoh's absolute authority and his administration's logistical machine broke down, the continuous, generational projects became impossible. The social technology of mass labor dissolved, and with it, the precise choreography for moving megaliths was lost, even if the basic physics of levers was still understood. A parallel shift occurred with changes in religious and cultural priorities. The New Kingdom pharaohs abandoned giant pyramids for hidden, rock-cut tombs in the Valley of the Kings. The spiritual focus moved from a monumental stairway to the stars to secret, underworld journeys. This theological shift meant the driving purpose for moving multi-ton stone blocks evaporated overnight. The master builders adapted their skills to new forms, carving intricate reliefs in tomb walls rather than hauling obelisks, and over generations, the old quarrying and transport law simply atrophied from disuse. In the Roman world, a technological revolution provided a more efficient alternative, concrete. Why spend decades quarrying, shaping, and moving 1,000 granite columns when you could mix volcanic ash, lime, and rubble to pour an arch, a vault, or an entire dome in a fraction of the time? Concrete was faster, cheaper, and more flexible. As it became the material of choice for empire building, the profound, patient knowledge of stone became a specialized art for luxury projects, not a fundamental pillar of construction. The economic and social cost of megalithic projects ultimately made them unsustainable. They required a staggering diversion of resources, feeding and managing thousands of non-agricultural workers for decades. As societies faced new pressures from climate shifts to external conflicts, such extravagant investments became impossible to justify. The knowledge did not disappear in a fire or a war. It was simply no longer funded, practiced, or passed on. It faded like a language with no more native speakers, not because it was invalid, but because the world that gave it meaning had changed. This is perhaps the most humbling lesson. Our ancestors' greatest engineering feats were not maintained by a secret library, but by a continuous, living tradition of practice. When the practice stopped, the deepest nuances, the tricks of the trade learned over centuries, evaporated into the air, leaving behind only the silent, impossible stones and our enduring wonder at how they ever came to be. A modern civil engineer standing before the 800-ton stones of Baalbek would not see a supernatural mystery. They would see a masterclass in applied physics, a monumental exercise in solving the fundamental equations of force, friction, and material limits. The ancient builders may not have written out formulas, but their every decision reveals an intuitive, hard-won mastery of the principles that still govern engineering today. Take the concept of statics, the study of forces in equilibrium. When they levered a stone upward, they were instinctively calculating moments. The long timber, the carefully placed fulcrum, the collective weight of the pullers, all were variables balanced in a mental model to achieve that first, crucial inch of lift. They understood that to move a mass, you must first overcome its inertia, and that a small force applied over a great distance could defeat a large resistance over a short one. This is not magic, it is the pure, elegant logic of the lever, a principle so foundational it is taught in every introductory physics class. Their handling of friction is equally sophisticated. The act of pouring water or oil before a sledge runner is a direct intervention in the coefficient of friction. They observed that a lubricated surface drastically reduced the resistive force, allowing a given team of pullers to move a much heavier load. They were, in effect, conducting real-world experiments in tribology, the science of interacting surfaces, and arriving at the optimal solution with the materials at hand. Even their choice of materials speaks to an empirical understanding of material science. They selected Dolerite Pounders not at random, but because through trial and error they discovered it was harder than the granite they needed to shape. They used quartz sand as an abrasive because they recognized it was the hardest common mineral available, turning the stone's own strength against itself. This represents a profound grasp of relative hardness, a key concept in materials engineering. The precision of their joins, especially in places like Sacsayhuamon, demonstrates an intuitive feel for load distribution and structural integrity. Those interlocking polygonal blocks are not just artistic, they are brilliantly seismic. The complex interfaces distribute stress across a vast network of contact points, preventing cracks from propagating and allowing the entire wall to flex as a unified mass during an earthquake. A modern engineer designing a shear wall or a dam employs similar principles, using shape and fit to manage immense forces. So what does this perspective give us? It reframes their achievement from a question of lost technology to one of brilliantly observed and applied natural law. They were the ultimate practical physicists, their laboratory the quarry, their equations written in rope tension and lever length. They did not have calculus or computer models, but they had generations of keen observation, patient experimentation, and the relentless drive to find what worked. This view does not diminish their genius, it grounds it in something even more remarkable: the human capacity to decode the rules of the physical world through hands-on engagement, and to wield those rules on a scale that still leaves us breathless. The shimmering temples and silent giants we admire today cast long shadows. For every stone perfectly placed, there was a cost, a profound expenditure measured not just in years, but in the very landscape and lives of those who built them. To truly understand these achievements, we must also acknowledge the immense toll they exacted, the sustainability question that lies at the heart of their grandeur. The first and most visible impact was on the environment itself. Consider the sheer volume of timber required. Moving an 800-ton block on rollers is not a one-time event. It is a constant, rolling consumption of wood. Each log, a mature tree, would be crushed under the weight after a few dozen yards of travel, then rushed to the front to be crushed again. For a journey of half a mile, this represents a small forest sacrificed for a single stone. Multiply that by the millions of blocks in a pyramid complex, and the scale of deforestation becomes staggering. Entire hillsides were likely stripped bare, not just for rollers, but for the massive sledges, the levers, the scaffolding, and the fuel for the fires used in quarrying and for feeding and sheltering the workforce. This was an economy of consumption on a scale that would reshape local ecologies for generations, turning wooded areas into barren slopes and altering microclimates. The human cost is a more delicate subject, one we must approach with respect for those whose names are lost to history. The popular image of whip-driven slaves is largely a myth, but that does not mean the labor was without hardship. The work was brutally physical and dangerous. A slipping lever or a snapping rope under thousands of pounds of tension could mean catastrophe. Quarry work sent constant shards of stone flying, risking injury to eyes and lungs from the perpetual dust. The long-term physical toll on joints and muscles from a lifetime of swinging stone hammers or hauling on ropes is almost unimaginable to us today. While evidence from workers' settlements at Giza suggests they received medical care and were valued, the sheer scale of these projects means that loss of life was an inevitable part of the endeavor. Accidents, illness from close quarters living, and the cumulative strain of a lifetime of such labor would have been a quiet, constant reality. This presents us with a difficult duality. We can marvel at the organizational genius that fed and housed thousands, that created a society capable of such unified effort. Yet we must also recognize that this very organization was built to marshal human beings toward a task of almost unbearable difficulty. The spiritual motivation, the belief in a cosmic purpose, provided meaning and likely voluntary participation for many, but for others it may have simply been a duty, a labor tax required by the state, a season of back-breaking work far from home. The legacy is thus a complex tapestry, woven with threads of both profound human aspiration and profound human exertion. To see only the suffering diminishes the meaning they found in the work. To see only the glorious result ignores the price paid to achieve it. The true picture lies in holding both truths at once, understanding that these stones are monuments not only to what humanity can build, but also to what humanity can endure in the name of an idea greater than any single life. They stand as a permanent question about the balance between collective ambition and individual cost, a balance every great civilization must ultimately weigh for itself. Even with all we have reconstructed, certain details of their work remain stubbornly out of focus. The most brilliant engineering leaves behind not just answers, but a deeper layer of questions, puzzles so precise they seem to taunt us with their perfection. Take, for example, the granite boxes in the Serapeum of Saqqara, Egypt. These are not ordinary sarcophagi, but massive containers carved from single blocks of granite, each weighing around 70 tons, with lids so heavy they themselves weigh many tons. The mystery is not their weight, but their interior geometry. The inside corners of these boxes are perfectly sharp, 90-degree angles, meeting with a precision that seems impossible to achieve with hand-held tools. How did a worker, swinging a stone pounder or even a copper saw in a confined space, achieve such a flawless internal corner? The tools we know they had could create smooth surfaces, but a perfect interior vertex is a different challenge altogether. It suggests either a level of skill with abrasives we have yet to fully replicate, or perhaps the use of a specialized guiding tool, a kind of interior square or template that has left no trace in the archaeological record. This is not a question of scale, but of micro-precision, a whisper of a technique we have not yet heard clearly. Across the ocean, at the Inca site of Ollantaytambo in Peru, another transport mystery defies simple explanation. High on a mountainside, 6 colossal monoliths known as the Sun Temple stones stand in a row. They are made of red porphyry, a stone even harder than granite, and each one weighs well over 50 tons. The quarry for this stone is located on a different mountain, across a deep valley and a roaring river. The established theory involves an elaborate system of earthen ramps, but the incline from the riverbed up to the temple site is extraordinarily steep. The logistical challenge of pulling such masses up that final, severe slope, even with thousands of pullers, pushes the limits of known friction physics. Some researchers have proposed an alternative, that the stones might have been moved during a period of catastrophic flooding, using the immense power of water itself to help lift them. But this remains a speculative and highly debated idea. The path these stones took is still walked by archaeologists today, searching for the faintest imprint of a ramp or the telltale wear marks that could finally map their impossible journey. Perhaps the greatest ongoing puzzle is not a single stone, but a sequence, the exact choreography of the pyramid's rise. We know ramps were involved, but their specific configuration at each stage of construction is a subject of vibrant, sometimes heated, academic debate. The straight ramp theory, while logical for the early stages, becomes a monster of its own making by the final tiers. The spiral ramp theory is elegant but creates serious problems for maintaining the pyramid's precise geometry. In recent years, a third idea has gained traction, the internal ramp theory. Proposed by French architect Jean-Pierre Houdin, it suggests that after a large external straight ramp was used for the bottom third of the pyramid, the builders switched to a corkscrewing ramp built inside the pyramid's own structure, tunneling upward within the already placed blocks. This would explain the absence of massive ramp rubble at the site and could account for the accuracy needed for the upper courses. To test this, teams are now using non-invasive technologies like microgravimetry and infrared thermography, scanning the Great Pyramid for hidden voids or density variations that might reveal the ghost of an internal spiral passage. This is cutting-edge archaeology, using cosmic ray detectors to essentially take an X-ray of a 4,500-year-old monument, hoping to see the shadows of the builder's final, hidden road. The focus of modern research, therefore, is shifting from grand theories to forensic detail. It is in the microscopic analysis of tool marks, using three-dimensional scanning to map the exact striations left by a copper saw and determine its angle and stroke. It is in the experimental reconstruction of specific, puzzling tasks, like trying to replicate that perfect interior corner of the Serapeum boxes with period tools. It is in the painstaking environmental archaeology that studies ancient pollen and soil samples around quarry roads, searching for evidence of the specific plants used for ropes or the lubricants poured before sledges. Each unanswered question is now a narrow beam of light, guiding researchers to look closer, not just at the stones, but at the dust between them, the chemistry of the rock surface, and the subtle scars left by a process that was, to its creators, simply the way things were done. The silence of the past is not absolute. It is a quiet hum of data waiting for us to learn how to listen. Granite did not surrender easily, but it did surrender. The story of these megaliths is not one of a single magical breakthrough, but of 1,000 small victories. Ancient engineers triumphed by mastering a simple yet profound truth. They did not fight the stone, they collaborated with it. They listened to its natural fractures, harnessed the swelling power of wood and water, and turned its own crystalline strength against itself with simple abrasives. Their genius lay not in complex machinery, but in the elegant application of basic physics: levers to multiply force, rollers to conquer friction, and ramps to trade distance for effort. This was a toolkit of breathtaking simplicity wielded on a staggering scale. Yet the true engine was never just the lever or the rope, it was the collective human spirit. These achievements were powered by a symphony of coordinated effort, by societies that could organize thousands of hands toward a single, generational vision. Whether driven by divine duty, ancestral reverence, or cosmic alignment, that shared purpose provided the unwavering will to endure projects that spanned lifetimes. The stones teach us that the boundary between the possible and the impossible is not fixed by technology, but by imagination, patience, and our ability to work together. They stand as eternal reminders that the most powerful force on Earth is a focused human community. So what do you believe? Do you have a favorite megalithic mystery, or a theory about how a particular stone made its journey? Share your thoughts in the comments below, and let's keep the conversation with these ancient builders alive.